Dr. Simon Shim from San Jose State University. Let me introduce him. He's a professor in the computer engineering department at San Jose State University. And with a strong background in research and teaching, he has published over 50 papers in leading journals and conferences. And before joining SJSU, Dr. Shim worked as a director at SAP Labs, where he contributed to advancements in in-memory databases. He has also served as an editor for IE Computer, focusing on key topics like high-speed security and next-generation memory. And currently, his research centers on internet computing, database management, machine learning, and information retrieval. Dr. Shim holds a PhD in computer science from University of Minnesota. With that, I'll hand it off to you.
Thank you. Thank you thanks for a great introduction. I'm actually working for applied data science now, not a computer engineer anymore, so just one minor correction. All right. So this talk is about how to build an agent. So I think a previous talked about, give an agent, this is what they can do, okay? But there are a million different ways. Probably we counted around 60,000 different ways to build a RAG and agent. And then we're trying to see what are the good combinations. So this is a work actually I work with my students that actually, doing the measurements as which of the technique will give you how much better performance. So I don't know all your background, so I'll just talk a little bit about LLM. You probably heard about the LLM. Maybe I skipped this. But the LLM is where you can actually input a bunch of text, and then the LLM itself will understand the context and answer any question that relate to that documents. So if current trend is that the context window is getting bigger and bigger. I think a Gemini Pro they released this year can take up to 2 million tokens, so which actually means multiple books, not just one book. Could be a series of books. You can input as a one context window, and then you can ask any questions about it. So I think this is a really powerful technology, and then many of the companies are adapting this LLM as a form of agent because they have their own domain knowledge, and somehow they want to be able to serve this domain knowledge to the customers. So I have seen actually many of the conferences I attended, and then they actually show all these different applications of using LLM and agent. But there are, I told you, like 60,000 ways of building one. So how do they build it is a topic for today. So how to build an AI agent is through you need to first define the role. So what is an agent is going to do? And then what are the data sources? What are all the documents you want to load into the agent so that it can service questions from customers? And what are the actions? What are the goals? What are the guidelines? And how to integrate to your software infrastructure. So those are the guidelines for how to build an AI agent. And then when you want to build an agent, you need to basically adapt to LLM to build all of these, right? So prompt engineering, you guys probably know what prompt engineering means. Depending on how you ask a question, you may get a good answer, you may get not a good answer, okay? The best way, again, as far as I know, the best way to learn how to use prompt engineering is you need to continuously conversation with LLM so that it can actually build up the background and then give you better answers. So that's a prompt engineering. Fine-tuning is you can actually fine-tune LLM model based on your domain knowledge. So this LLM is trained for general knowledge, probably trillions of, 5 trillion tokens, right? And then those are for general purpose LLM. But if you wanted to specify your certain domain, let's say a customer support, right? Then there are a couple ways of fine-tuning it. You actually giving your domain knowledge to LLM so that you can actually do a fine-tuning. So there are some techniques. You can do a pre-training. You can do LoRa. You can do a QLoRa. So basically, you can do fine-tune the LLM itself so that it actually acquires some domain knowledge. And then the other technique, a well-known technique is RAG, Retrieval-Augmented Generation. So RAG is you're actually building a database of the knowledge, domain knowledge. And then whenever a customer asks a question, and then you take this question and then trying to match with your database. When there's a good match, it'll give you very good context, okay? But the assumption is you're actually getting a good context from this database. Oftentimes, you may not get good context. You may get some random match. And then your response may be not so good. So we will talk about those. And then we'll agent and train from scratch. So again, train from scratch, these typical LLM models are huge, requires probably 10,000 GPUs. So probably it's not feasible for any good size of companies, right? So most people basically use either fine-tuning or using the RAG. So let me explain the RAG, Retrieval-Augmented Generation. So what it does is you give a bunch of documents, which is domain knowledge, right? You give a bunch of documents, and those documents is chunked. So you basically divide into small chunks so that you can put it into vector DB. And once you make a good chunk, again, this chunk has to be semantically make sense. You cannot just do a random chunking or based on period. You need to do semantic-based chunking. And then once you do the chunking, then you convert this chunk to embedding. So embedding means because computer doesn't understand the word, right? You actually convert into numbers. So these numbers is actually stored as a vector. It's stored into the database, vector DB, okay? Once it's stored in the database and user send the query, this query is also vectorized. And then you send this vector to the vector DB and then do a similarity search. It could be a cosine similarity. It could be similar type of similarity search. Once you do a similar search, and then you will find a match. It will return many results, many similar results back to LLM. So this LLM can actually get this relevant information. For example, if you're asking a question about the customer, certain products, right? The LLM doesn't know about the product, right? But about the product information, you actually retrieve from the vector DB, and you feed the product information plus the question to LLM, so they actually understand what the product is. So that is basically RAG, and then it'll basically generate answers, and then the customer is served. Okay, so basically the steps: document loading, splitting, embedding, storage, and then your query. Your query is actually sent to the vector DB, and then vector DB returns the relevant information about the query, and then build a prompt and send to LLM, and then the answers. So this is the process that most of the LLM agents are built. Okay, but the question is, how do you build well so that 99% of the time you will get relevant answers? So that is a challenge. And I mean, anybody can build a RAG, but if you build a RAG, you may be disappointed because your accuracy is pretty low. It's like 60%. I can guarantee if you just build it without knowing much about how to build the RAG, I think your accuracy is around 60%. So, so this is how you can do an embedding. The words are too small that I cannot read it. But anyway, the embedding basically means you convert your sentence into a vector, which is number, okay? And then so that you can actually store that vector into the database. And these are most widely used vector store. There are many vector stores available today. Some are good, some are not so good. So that's why I bring this LangChain State of Art 2023. Someone actually did a ranking on it based on how often they used. So number one is Chroma, Vice, Pinecone, Quadrant, etc. So those are your choices then how you can build a vector DB. Fine-tuning is called parameter efficient fine-tuning, is selectively update parameters. So you have general LLM, right? You want to fine-tune in your domain. So that means you want to leave most of the weights intact. But you update small portion of the weight has to be updated based on your domain knowledge. And that is what fine-tuning does. Because if you do a retraining with your domain data, then it's likely that the LLM doesn't work. So it'll actually break all the right weights, and then suddenly answer different things. So the performance goes down. So we don't want to do that. We want to do only small portion of the weights has to be trained. And those are well-known techniques in fine-tuning. So in terms of parameter, so we are doing parameter tuning, right? So what is a parameter means? If you know the neural networks, if you know the weights, and then you know the biases, and those are what is called parameters. So whenever you call it LLM parameters, let's say you have 7 billion parameters, and those are numbers of weights and biases. So, there are many different LLM, 7 billion, 64 billion, 32 billion, et cetera. Those are all these parameter numbers. So in terms of fine-tuning, we have what is called low-rank adaptation of the language models. So basically, this means you freeze a weight of pre-trained LLMs, and then you create low-rank matrices. So this is your fine-tuned weights. And these fine-tuned weights are low-rank. So that means you don't keep all the weights, right? You do SVD decomposition, and you keep only a small portion of it. So they can multiply these two matrices. You can get the original matrices. So that's what is called LoRa. And then QLoRa go one more step, actually making a chunking, making it like a 4-bit instead of 8-bit. So even your weights become small number of bits. And then they use what is called the normal distribution. So they use a normal distribution to actually do the 4-bit low precision. Okay? And the original LLM probably takes 10,000 GPUs. LoRa probably takes 16 GPUs. QLoRa, you can run it on 1 GPUs. And then the paper showed that the performance is similar to the original LLM. So I think this is really an important way to fine-tune LLMs. And this is what the method that we use in our study. So before we show the result, we show you what kind of data set we used. So we use basic skincare products. We scrape the data from the web and then data world, and we also remove all the duplicates, right? Clean the data, remove all the images and special characters. And then we have the chunk size around 2,000 and overlapping 200 characters, because we want to have continuation of the chunk so that it can has some semantic meanings. So this overlapping is kind of common techniques. So embedding, text embedding 3 large OpenAI dimensions. There's a 4,000 index vector counts, and then we use a quadrant vector database. And then Neo4j for graph database. So knowledge base, knowledge graph is probably is very well known. I think I saw some of the sessions that coming from Neo4j. So you're building knowledge representation. For example, if you say a person eats lunch, right? You can actually build a graph saying person is an object, is a lunch, the relationship between lunch and person. So those are the, even though this is obvious for human, it may not be obvious for LLMs. So you can build these knowledge graph with knowledge base so that, okay, maybe we should skip this. Okay, so the RAG approach, we experiment with many different types of RAG approach. For example, like a multi-query. So that means you ask one question, right? We generate 3 different questions that relate to that original question. So instead of asking one question, we ask 3 questions. So here's the example of the question we actually ask. It's called multi-query RAG. And then re-ranker is when it returns a result, we can actually re-rank. So there's another LLM you can ask, are these contents, are these retrievals relevant to the question that they are asking? So you actually do a re-ranking, and then you can build a graph database. And then when you service, you actually do a search on this GraphDB, and then find the relevant entities and relationships, and you give that relevant information with your query to LLM so they understand what is the knowledge base. And then Fusion RAG is basically combining multi-RAG plus re-ranking. So we prepare these 400 pairs of Q&A for evaluation. And then the metrics are relevance, similarity, correctness, faithfulness, and then precision, and then recall. So we'll give you some result. Kind of small, but it's actually showing the naive RAG versus multi-query or re-ranker. So as you can see, so you actually improve the accuracy and then also other metrics. But again, the improvement is not dramatic, but again, there is improvement. And then this one shows Fusion. So Fusion is basically combining multi-query plus re-ranker, and then actually give you a much better result than the previous result. So if you combine those, right, it'll give you a much better result. So graph RAG actually can improve the correctness much better. And then this is a self-reflective RAG, so that basically means before you output the answer, you ask LLM whether this input, this question and the response is making sense. So you're actually using one more filter before you send your response. It'll actually use a code called the self-RAG. So this actually can improve the correctness more than the other techniques. And then this is a performance. We have 2 minutes. This is performance we're showing how the fine-tuning actually works, right? So fine-tuning actually improves the answer relevance, which is correctness. You can see that Llama 2, 0.94, and then Llama 2 with a QRORA, and then fine-tuning improved to a 1. So there is an improvement. So the conclusion is, so RAG is generally improved the modern performance, okay? And graph RAG offers superior performance. And then the retrieval-augmented fine-tuning, which is RAG plus fine-tuning. So if you can combine fine-tuning plus RAG, right? And it'll give you much better result than original rag. So the conclusion is that we should recommend combining those two, which gives you a much better result than original rag. And then we also recommend using graph rag in addition to the self-reflection. So those 4 different techniques will improve the accuracy much better than your original rag. So this is the study that we did. And the future work is role-based multi-agent collaboration with rag. So this rag we build, you can apply that as an agent. So each of the rag will have certain roles, certain domains. For example, someone is a product manager, someone is a CEO, someone is programmers, and then they have different roles, and they have their own domain knowledge. So you can actually train those different roles as an agent. And then you can use all these techniques to improve the accuracy. And based on that, you can actually build the whole, what do you call the workflow. So you can build a workflow based on agent techniques. So that is my conclusion, and then I'm on time.